level of take this value and write it onto this tape. First of all, we don't have tapes anymore in computers. Even if we did, you don't want to be programming it. What we're going to see with programming languages is we're going to use higher level abstract, a broader set of primitives, but nonetheless the same fundamental thing. With those 6 primitives, you can do it. Okay, so where are we here? What we're saying is, in order to do computation, we want to describe recipes, we want to describe this steps, built on some primitives. We want to describe the flow of control that goes through those sequence steps. So the last thing we need before we can start talking about real programming is we need to describe those recipes. Right? And to describe the recipe, we're going to want the language. So not only what are the primitives, but how do we make things meaningful in that language? There we go. Alright. Now, it turns out there are, I don't know, hundreds, thousands of programming languages, at least hundreds of programming languages around. True. Thank you. They all have, their pluses and minuses. I have to admit, in my career here, I think I've taught at least 3 languages. I suspect you've taught more, 5 or 6 taught. Most of us have probably programmed in more than those number of languages, at least programmed that many, because we talk about languages. One of the things you want to realize is there is no best language. I would argue that, I think John would agree. We might both agree we have our own nominees for worst language. There are some of those. There is no best language. They all are describing different things. Having said that, some of them are better suited for some things than others. Anybody here heard of MATLAB? Maybe programmed in MATLAB? It's great for doing things with vectors and matrices and things that are captured in that framework. But there's some things that are a real pain to do with MATLAB. MATLAB's great for that kind of thing. C is a great language for programming things that control data networks. I happen to be, and John teases me about this regularly, I'm an old-time list programmer. That's the like list to me. Not having the like list and scheme is a great language when you're trying to deal with problems where you have arbitrarily structured data sets. And so the point I want to make here is that there's no particularly best language. What we want to do is simply use a language that helps us understand. So in this course, the language we're going to use is Python. It's a pretty new language. It's growing in popularity. It has a lot of the elements of some other languages because of course it inherits things from its progenitors, if you like. But one of the things I want to stress is that this course is not about Python. Strange thing, you do need to know how to use it, but it's not about the details of where the semicolons go in Python. Right? It's about using it to think. What you should take away from this course is having learned how to design recipes, how to structure recipes, how to do things in mode, in Python, those same tools easily transferred to the other language. Pick up another language in a week, a couple of weeks, once you know how to do Python. Okay, in order to talk about Python and languages, I want to do one last thing to set the stage for and that's to talk about the different dimensions of a language. There are 3 I want to deal with. The first one is whether this is a high-level or low-level language. That basically says how close are you to the guts of the beast. The low-level language, we used to call this assembly programming. You're down at the level of your primitives or literally moving the data from one location to everything else. A very simple operation. A high-level language, the designer has created a much richer set of primitive things. In a high-level language, square root would simply be primitive rather than you have to use code. And there are trade-offs between both. Second dimension is whether this is a general versus a targeted language. By that I mean that a set of primitives supports a broad range of applications for it really needs and a very specific set of applications. I'd argue that MATLAB is basically a targeted language, targeted in matrices, vectors, and things like that. And the third one I want to point out is whether this is an interpreted style language. What that basically says is the following. In an interpreted language, you take what's called the source code, the thing you write. It may go through a simple checker, but it basically goes to the interpreter, that thing inside the machine that's going to control the flow of what's going giving output. So the interpreter is simply operating directly on your code at runtime. In a compiled language, you have an intermediate step, which you take the source code, runs through what's called a checker or a compiler or both, and it creates what's called object code. And that does two things. One, it helps catch bugs. Secondly, it often converts it into a more efficient function before you actually go off the code. And there's trade-offs between both. In an interpreted language, it's often easier to debug. There's your raw code there, but it's not always as fast. Compiled language is much faster in execution. It's one of the things you may want to trade off. Right, in the case of Python, it's a high-level language. I would argue, I think Tom would agree with me, it's basically a general purpose. It happens to be better suited for manipulating strings than numbers, for example, but it's really a general purpose language. And it's primarily interpreted. Okay. As a consequence, it's not as good at helping debug what it does when you perform it. It's not as good at catching something before you run them. It is easier sometimes to debug as you go along on the fly. Okay, so what does Python look like? Go to the top of Python. We need to talk about how to write things in Python. Again, let me back up slightly and set the stage. Our goal is to build recipes. We're all going to be great chefs by the time you get here. Our goal is to take problems and break them down into computation systems, sequence of instructions that allow us to capture that problem. To do that, we need to describe not only what are the primitives, but how do we capture things safely in that language and interact with the computer. For that, we need a language. We're about to start talking about the elements of the language, but to do that, we also need to separate out one last distinction. Like with a natural language, we're going to separate out syntax versus semantics. So what's syntax? Syntax basically says, what are the legal expressions in this language? There's an English sequence of words. It's not syntactically correct, right? Not a sentence. There's no verb in there anywhere. Just fix the noun. Same thing in our languages. We have to describe how you put together legally formed expressions. Okay? And as we add constructs to the language, we're going to talk about that. Second thing we want to talk about very briefly as we go along, the semantics of the language. And here we're going to break up two things, static semantics and full semantics. Static semantics basically say which programs are meaningful, which expressions make sense. It's an English sentence. It's syntactically correct. Right? Noun phrase, verb, noun phrase. I'm not certain it's meaningful unless you are in the habit of giving your furniture personal names. What's the point? Okay, you can have things that are syntactically legal but not semantically. Static semantics is going to be a way of helping us decide what expressions, what cases don't actually have real meaning. Right? The last piece of it is, in addition to having static semantics, we have full semantics. What does the program mean? Said a different way, what's going to happen when I run it? What's the meaning of the expression? That's what you want. Like you want to know what's the meaning of this piece of code. When I run it, what's going to happen? That's what I want to build. The reason for pulling this out is what you're going to see is that in most languages, and certainly in Python, you get lots of help here. Okay, Python comes built in with something that will check your static, sorry, your syntax for you. In fact, in the sidebar, if you turn in a problem set that is not syntactically correct, there's a simple button you push that will check your syntax. If you turn in a program that's not syntactically correct, the EA will give you a 0. Instead, you didn't even take the time to make sure the syntax is correct. The system will help you find it. In Python, it'll find it, I think, one bug at a time, right? Notify one syntax error at a time. So you have to be a little patient too, but you can check that is right. You're going to see that we get some help here. Static semantics, we're not doing examples. Meaning that the system, some languages are better than others on it, but it will try and help you catch some things that are not exactly correct. In the case of Python, it does it, I think, all the runtime. I'm looking at you here, John. I think there's no pre-time check. Sorry. There is some, okay. Most of them, I think, are primarily caught at runtime, and that's a little bit of a pain because you don't see physical and running code. There are some that I'm going to see an example of in a second, but you do get some help there. The problem is, things that you catch here are actually worse to us. They're easy to spot. You can't run the program there, so you're not going to. Not everything is going to get caught. That is something we're going to slide through. That's actually the problem. As I said, your program still gives you a value, but it may not be what you intended. You can't always tell, and that may propagate its way down to a whole bunch of other computations before it causes some catastrophic failure. So actually, the problem with static semantics is you like it to catch everything still going through. Sadly, we don't get much help here. It's hardly like it, but that's part of your job. Okay? What happens is you actually have something that's both syntactically correct, that appears to have correct static semantics, and you run it. It could run and give you the right answer. It could crash. It could loop forever. It could run and apparently give you the right answer. And you're not always going to be able to tell. Well, you'll know when it crashes. It doesn't help you very much. But you can always tell whether something's stuck in an instance or whether it's just taking a long time to compute. You'd love to have a system that spots that, which is not possible. So to deal with this last one, you need to develop files. Right? Meaning, we're going to try and help you with how to develop good programming style, but you need to write in a way in which it is going to be easy for you to spot the places that cause programming bugs to occur. Alright. Sounds like a really long preamble. It is. Let's start with Python. Again, my goal here is to let you see what computations about why we need to do it. I'm going to remind you one last time. Our goal is to be able to have a set of primitives that we combine into complex expressions we can then abstract between these primitives. And we want to use that sequence of instructions in this flow of controlled computing in order to deduce that imperative knowledge talked about right there. So I'm going to start today. We have about 5 or 10 minutes left, I think, in order to put 5 minutes left in order to do this with beginning with Python. I'm going to read and pick this up, obviously, next time. So, simple parts of Python. In order to create any kinds of expressions, we're going to need values. Primitive data elements. In Python, we have 2 to start with. Numbers. We have strings. Numbers is what you'd expect. There's a number. Another number. Right? Strings are captured in Python with an open quote, some sequence of characters, followed by a quote. Associated with every data type in Python is a type, which identifies the kind of thing it is. Some of these are obvious. Strings are just a type on their own. So for numbers, for example, we can have a variety of types. So this is something that we would call an integer, or an int. Something we would call a floating point or a float. You want to think of it as a real number. We're going to build up this taxonomy, if you like, but the reason it's relevant is associated with each one of those types. A set of operators that expect certain types of input in order to do their job. Given those types of inputs, you back output. Alright, in order to deal with this, let me show you an example that comes up great. What I have here is a Python shell. I'm going to just show you some simple examples of how we start building expressions. And this will lead into what you're going to see next time as well. So, starting with the shell, I can type in expressions. Actually, let me back up. Type in a number. Type in a string. Get back to string. Strings module where you can have spaces. Another character that's simply sequence of notice, by the way,